In this short video, we'll look at drawing asymptotic Bode plots by hand. Here you have a transfer function. It has 0 at the origin, a real 0 at -10, and a complex pole. The first step is to rewrite the transfer function to separate out the Bode gain, and this is how the end result looks like. What I've done is essentially brought this 10 out like so. So I have to divide this s by 10, and then I brought out 2500 out like so. So I have to divide the entire thing by 2500 here. So I've written this, 2500 happens to be 50 squared. So I wrote this as s divided by 50 the whole squared. And this 50 here, I've written it as 2 times 0.5 times 50 divided by 2500 times s. Now, this happens to be your omega n, natural frequency, and this, I'm writing this 50 as 2 zeta omega n. So 50 equal to 2 times 0.5 times 50. So this 0.5 here is zeta, the damping constant. Now let's look at drawing the gain of the transfer function. The gain of the transfer function is usually drawn on a semi-log plot. Here the x-axis representing the frequency of the input signal in radians per second is on a log scale. The y-axis, which is the magnitude, is linear, but the magnitude itself is represented in decibels. First thing we do is look at the Bode gain, write it in decibels. So in this case it happens to be 26 decibels. You get it in decibels by taking the 20 log to the base 10 of the magnitude. So that's your 26 decibel line right here. Next we look at the 0 at the origin. 0 at the origin crosses the 0 decibels line at 1 radian per second right here, and then it maintains a slope of 20 decibels per decade. So we draw that, crosses the 0 decibel line at 1 radian per second, and it has a 20 decibels per decade slope. So 1 decade down is from 10 to the power of 0, which is 1, is 10. So here it is 0 decibels, here it should 20 decibels. So 20 decibels per decade, and you draw the line. The real 0 has amplitude equal to 0 until the corner frequency, which is 10. That's a 10 here, 10 here, and then it goes up at 20 decibels per decade. Same thing, you go 1 decade forward right here and then count 20 decibels, mark that point and draw that line. The complex pole has 0 amplitude till the corner frequency, which is omega n. In this case it is 50, so this is 10, 20, 30, 40, 50, and then it dips down at 40 decibels per decade. So this is 50, you look 1 decade down, which is 500, so this is 100, 200, 300, 400, 500, and go down 40 decibels. So 10, 20, 30, 40, mark this point, join this point, and draw this line. This is dipping at 40 decibels per decade. Now, to get the resultant Bode plot, all you do is look at various corner frequencies and add up all the component magnitudes and mark the sum. So since all of these are straight lines, the resultant also is going to be a bunch of straight lines. So let's start at the first frequency here. You add up everything, so that here the magnitude of the 0 at origin is given by 20 log to the base 10 of omega. So in this case it is minus 20 decibels. Both these, the real 0 and the complex pole, have 0 magnitude at this point. Bode gain is 26. You add everything together, you get resultant 6 decibels. You go to the first corner frequency, which is omega equal to 10, and at this point you add up everything. So at 10 decibels you add up everything. So the component given by the 0 at the origin is again 20 log to the base 10 omega. Omega is 10, so that's 20 decibels. Both the real 0 and the complex pole have 0 magnitude, and this is 26 decibels as before, so the resultant is 46 decibels. You mark that point and then draw that line. So this is the resultant Bode plot of the entire transfer function between these two frequencies. The next corner frequency is 50 radians per second. So you add up all the component magnitudes. The contribution of the 0 at the origin is 34 decibels. The contribution of the Bode gain is 26 decibels. The contribution of the real 0 is 20 log to the base 10 omega divided by A. So that is 20 log to the base 10, 50 divided by 10, which is 14 decibels. You add up everything, you get 74 decibels, and then you draw this resultant line going from here to here. And after that, there doesn't seem to be any cutoff frequency. So what we can do is we can go here and add up all the contributions at the end, right here at 10 to the power of 3 radians per second. So the contribution of the 0 at the origin is 60 decibels. The contribution of the Bode gain is 26 decibels. The contribution of the real 0 is 40 decibels. And the contribution of the complex pole is minus 40 times log 10 log to the base 10 of omega divided by omega n. Omega is 10 to the power of 3 or 1000, and omega n is 50. That gives us minus 52 decibels, and if you add everything you get 74 decibels, and then you draw the final line. Now let's look at plotting the phase of the transfer function. Phase again is a semi-log plot with the x-axis in a log scale of frequencies, input frequency radians per second, and the y-axis is the phase in degrees. Now the phase contributed by the Bode gain, since this is a positive real number, is 0. The phase of the 0 at the origin is always 90 degrees, so mark that. Now the real 0 at minus 10, it's 0 until the first corner frequency, which is A by 5, which is 2. A is 10 here. It is 90 degrees from 5A to infinity. 5A, frequency 5A to infinity. 5A is 50, so it's 90 from 50 to infinity. In between it follows this line like so. For the complex pole, the first corner frequency is given by omega n divided by 5 to the power of zeta, with zeta is 0.5 here, omega n is 50, so this is nearly 22 radians per second. That's the first corner frequency. So the phase contributed is 0 till then. The second corner frequency is omega n times 5 to the power of zeta, which is nearly 111 radians per second. So the phase contribution from this corner frequency to omega equal to infinity is minus 180 degrees. In between it follows that straight line. Now for the total phase, all you need to do is look at various corner frequencies and add up the result. So you start with right here at the beginning here, add everything up. The phase contributed by the 0 at the origin is 90 degrees. Both these, the red and green, corresponding to the 0 at minus 10 at the complex pole, is 0 degrees, so the total is 90. Then you go to the first corner frequency, which is 2 radians per second, and then you add everything up. Once again, there is 90 from 0 at the origin, and both these are 0. Add everything up, the result is 90. Then you draw this line that connects this point to this point. Go to the next corner frequency, which is at 22 radians per second. Contribution of the 0 at the origin is 90 degrees. The contribution of the 0 at 10 is somewhere in between this line and this value is given by 90 degrees times log to the base 10 5 times omega divided by a divided by log to the base 10 25. Omega is obviously 22 degrees, a is 10, and this ends up being 67 uh, degrees. Contribution of the complex pole is 0. So add everything up, you should get 157 degrees. Now you can join these two lines to get that. Go to the next corner frequency, which is at 50 radians per second. Here this thing becomes the 0 at minus 10 becomes 0, and you add everything up. So this 290s, one is from the 0 at the origin, one is from the real 0 at minus 10, and the contribution of the pole at 50 degrees is given by minus 180 times log to the base 10 5 to the power of zeta times omega divided by omega n divided by zeta times log to the base 10 of 25. Zeta is 0.5, omega is 50, omega n is also 50, so this ends up being minus 90. Add everything up, you should get 90. Then you can join this line, and then finally there are no cutoff. There is one more cutoff frequency here at 111. So you count all the contributions here. So the 0 at origin contributes 90 degrees, the 0 at 10 contributes 90 degrees, and the complex pole contributes minus 180 degrees. This total is 0 degrees. So you can join that line like so. Now there are no more corner frequencies, so nothing else happens, so you can go to the end and add everything up. So the contribution here, because of the 0 at origin and the 0 at minus 10, is 90 each. This contribution is minus 180, add everything up, the total is 0, so you can draw this horizontal line like so. Now that is essentially your phase plot, asymptotic phase plot for this transfer function.